Hello to everyone. Hope you are doing all good in these strange times. My name is Grzegorz Kwiatek, and today I am going to show you a presentation titled Induced Seismicity ST1 shows limited earthquake interaction. Before proceeding, I would like to acknowledge the authors of this contribution, Patricia, Maria, Marco, and Georg from GFZ Potsdam, and also Matti Pentti from ST1 OI. The ST1 deep heat project I'll be going to talk today is located in Helsinki suburban area, 6 kilometers from Helsinki city center. This deepest EGS is composed of the well doublet, OTN2 and OTN3 that reaches the depth of 6 kilometers, and that both these wells are drilled into the Precambrian rocks. The developed EGS ultimately aims to provide a sustainable baseload for the local area heating network. In summer 2018, a first stimulation campaign has been performed in OTN3 well, and that led to over 60,000 earthquakes with local magnitudes ranging from -1.5 to 1.7. This stimulation was discussed extensively in our paper published in 2019, Science Advances. During injection operations, seismic activity was monitored in near real time and actively used to guide the injection operations. This ultimately helped us to limit the maximum magnitude below the red outlet magnitude threshold of 2.0. The analysis of the seismic data showed that seismicity follows basically stable pressure control models of maximum magnitude, such as those proposed by Gallis, Van der Elst, or Shapiro. Several elements actually contributed to the successful control of maximum magnitude at the project during 2018 stimulation. The key element was an adaptive injection strategy that was guided by, as I mentioned before, near real-time seismic monitoring that essentially limited hydraulic energy rate and consequently the elastic strain energy stored at any moment of the time in the geothermal system. Second was favorable structure of the reservoir and low background tectonic stress level. This includes lack of major fault system present in this area, with injection performed into a broad damage zone of distributed, parallel, and likely weak fractures. This has been discussed in the paper that was recently published by Leonhard et al. In Solidairs. Finally, our initial results revealed that we observe very limited spatial-temporal clustering of earthquakes. And this observation drew our interest in the sense that lack of such clustering could suggest limited stress perturbation coming from interactions between earthquakes. And this last point is actually a topic of my talk today. So in this presentation, I aim to discuss questions such as whether the ST1 seismicity responds solely to injection operations, or whether we observe any statistical or physics-based evidence for interaction between events. The existence of such interactions would suggest the presence of additional stress perturbation or stress transfer that is hardly controllable, contributing to the enhanced seismic hazard during injection. So I will focus on the analysis of the new induced seismicity dataset framing second stimulation campaign performed in May 2020. However, the obtained results are in agreement with ones obtained from 2018 stimulation, which is the subject of a separate work of our PhD student, Maria Leonhard. In 2020, over 3,000 cubic meters has been injected within the 2 weeks into the OTN2 well, which is approximately 6 times smaller volume than that injected in 2019 in OTN3. The injection pressures were lower by 20 megapascal in comparison to that used during 2019 stimulation. And well, not surprisingly, the seismic response was much lower in 2020 than in 2018, amounting to approximately 40 times less earthquakes detected above the same magnitude of completeness. During 2018 stimulation, spatial migration of the seismicity was visible outside of injection intervals at high wellhead pressure, but that seemed to be not the case for 2020 stimulation seismicity, which basically sticks to the injection well. This is likely to the lower injection pressure mentioned. The seismic energy release is proportional to the hydraulic energy input without any erratic disturbances during the both stimulation campaigns. To investigate the interactions between events, we selected the subset of the catalog containing three phases, S2, S3, and S4. And this period as a whole display a quasi-stationary seismic activity because between the stages you have that periods, basically two one-day lasting pauses in injections that visibly reduce the seismic activity in that time. Even a presence of these short-term non-stationarities does not influence the results I obtain that I will present in the following slides. However, what influenced the results a lot was significant temporal fluctuations in the completeness of the seismic catalog that biased calculated statistics and that essentially needed to be accounted for. So actually, to show you this better, I show you here the magnification of the plot in the background that is containing 2 days. And as you can see in that plot, the minimum magnitude is affected by the day-night noise cycles that could be modeled with the kind of sine wave. And in addition, noises from the injection pumps further reduce the detectability of the small events, leading to that kind of sawtooth-like pattern of the magnitude of completeness. And taking this all into account, we selected a rather conservative magnitude threshold for the completeness of the catalog, that is magnitude minus 1.25. First, what we did here, we calculated temporal evolution of the Gutenberg-Richter magnitude frequency p-value, which presents the proportion of between the number of large and small earthquakes. We found essentially that small-scale local fluctuations are within the uncertainties of the p-value estimation, and the temporal sequence of the p-values can be basically considered stationary here. Following the seminal work of Schultz from 1968, invariance of the p-value would suggest limited changes in the stress level at the reservoir. Or alternatively, while you follow another work of Ian Main from 1991, the stable development of the fracture network. From the perspective of seismic hazard, we have clear indications that the seismic hazard is controlled by the seismic activity level. In the following, we tested whether the selected catalog contains any signature of correlation between local magnitudes of consecutive events. If such a relation exists, one could predict earthquakes based on the magnitude of previous events, but also actually one can identify short temporal accelerations or decelerations of seismic energy release. We follow here using the methodology that was present, for example, in Davidson et al. And actually the two figures that you see here shows the difference in probability to observe the magnitude difference lower than m between the selected catalog and its randomized version, which do not exhibit magnitude correlations by default. The empirical distribution of magnitude difference that is shown with the dots here falls within 68% confidence interval with respect to the multiple generations of the randomized version of the input catalog that does not contain any magnitude correlations. That means that in the case of seismicity recorded during injection phases S2 to S4, we do not observe any signature of magnitude correlations, even despite the input dataset contains 2 periods of shut-in. The only statistically significant deceleration is visible after the final shut-in of the well. Finally, we investigated whether we observe any indications for temporal clustering of earthquakes, and for that purpose, we used the inter-event time ratio statistics that were initially proposed by van der Els and Brodsky. For stationary and slowly varying Poisson process, the PDF of inter-event time ratio is essentially flat between the 0 and 1. Clustering or anti-clustering of events in time is expressed by the significant deviations from that uniform distribution around 0 and 1. And this is actually shown on the 2 sample figures to the right, where actually the one figure shows the aftershock sequence of magnitude 2.1 earthquake that was recorded in South African gold mine, and the other shows the background and aftershock seismic activity that is observed in the alpine form. However, for the selected catalog that we are investigating, we observe the distribution of inter-event times fall within 95% confidence interval expected from the catalog with the same number of events, but randomly distributed over the time period, so essentially following the Poissonian process. This means that we do not observe any statistically significant clustering or anti-clustering of the seismicity, and the seismicity displays the characteristics of, well, background seismic activity. This also suggests that we have a limited stress transfer between earthquakes. To summarize this presentation, what we see is that the statistical and source properties of induced seismicity covering both stimulations at ST1 are quite comparable. From the point of view of statistical analysis, no indications for static and dynamic stress transfer between earthquakes is existing. And we suppose that the seismicity is basically a direct function of the injection operations and follows the quasi-stationary Poisson process. The seismic hazard and maximum magnitude are, from that perspective, controlled by the seismicity rate changes only, so the A value in Gutenberg-Richter relation, and likely linked to the hydraulic energy rate only. We have, if one consider the additional information of the structures in the area, we have essentially a limited possibility for runaway ruptures, and the seismic hazard assessment can be performed through the parallelistic methods. And well, the tapered Gutenberg-Richter distribution works just fine in our case. Finally, the technical aspect of that study is that it's very important for the statistics that we calculated to make them viable is to account for the rapid changes in the magnitude of completeness of seismic catalog. If you don't do this, your statistics will be certainly biased and may lead you to wrong conclusions. So with that, I would like to thank you very much for your attention. And if you want to contact me, here you have the contact data. And also, if you want to read something more about the ST1 project and our work there, you can visit my website. Thank you very much for your attention. I'm looking forward to your questions.